Hello everybody. So today we're going to have a look at Pythagoras Theorem, which is to do with triangles. This is video 1, which I've called the basics. So there will be a second video where I'll show you a quicker method for using Pythagoras with a calculator. But in this video I'm going to build it up from the very first principles, where I'll show you why it works, and you can join in yourself as well. So rather than me just telling you a formula and promising you really hard but it works, I'm going to show you why it does and that it does, so that you can actually see for yourself as well as me just telling you. So the first thing I'd like you to do, if you can, is to find some graph paper or squared paper like this, and once you do, if you could please draw a triangle which is 4 centimeters long and 3 centimeters high, and make sure as well, if you could do, that it's a right angled triangle. And so here's one I made earlier. So as you can see, it's 4 centimeters long. I've cheated and just made each square here exactly 1 centimeter. Your squared paper might well be different, so don't worry, but make sure yours is 4 centimeters long, like mine is, and as well, just check that it's 3 centimeters high. So after that, what we're going to do is measure the longest side, which is called the hypotenuse, to the nearest centimetre. And so, if you do this as well as me, write down what you get. On mine, hopefully you can see here yourselves as well, starts at 0, 1, 2, 3, 4, 5. And so, for my one, the hypotenuse is 5 centimetres long. So this is a 3, 4, 5 triangle. So I'm going to fill this in, and again, like I'm saying here, you should have found that the longest side was almost exactly 5 centimeters. So I'm going to record this down in this table. So what we're going to do, we're going to multiply the lengths of these sides by themselves, which just means squaring them. Then we're going to fill it into this table, like this one below. And so if you could make your own table, similar to this one. So the length was 4, the length squared is 4 times 4, which is 16. The height was 3, 3 squared means 3 multiplied by 3, which is 9. And the hypotenuse we measured was 5, square that, 5 times 5 is 25. And so that's the first triangle done. We're going to try and draw some more now as well. So next, try doing the exact same thing, but this time use a triangle which is 12 centimeters long and 5 centimeters high, and measure the hypotenuse as accurately as we can to the nearest centimeter, and let's see what this hypotenuse measures. So using this one here, and as well check yourselves your own triangle too, so it's not just me cheating. If I start from 0 and measure along this top edge, which is the hypotenuse, mine looks to be 13 centimeters to the nearest centimeter. So if you look here, it's 12 long and 5 high. So I've not just made up these numbers. It was actually 12 long and 5 high. And we can say that this is 13 centimeters. And so what we need to fill in is again this table. But the length of it squared is 12 squared. So what's 12 times 12? If you can, try that without your calculator. But you should find that 12 squared is 144. For height, squared, 5 times 5 is 25. And hypotenuse squared, 13 squared. I'll let you off if you want to try that on your calculator. But you should find that 13 squared comes to 169. Like so. And moving on, let's just try one more. This one's a big triangle, 9 centimeters long, 12 high. Then we're going to measure the hypotenuse of this one as well. So If we check this one over here, now you should find, if you draw one which is 9 long and 12 high, that it comes to exactly, or pretty much exactly 15 centimeters. So I'm going to label this one here. So that's 15 centimeters. And so again, filling in this table, the length squared, 9 times 9 is 81. The height squared, 12 times 12 is 144. And if you square the hypotenuse, which is 15, 15 times 15 is 225. So you might be thinking, well, why are we doing this? The idea is to see if we can spot a pattern. So having done these 3 triangles, let's have a look and see if we can notice anything between the length squared, the height squared, and this red number, hypotenuse squared. Do you notice anything for each row? So if you want to pause the video and just have a think yourselves before I spill the beans and spoil the secret, try and think if you can spot a pattern between these numbers. So pause it now, have a think if you can spot a pattern, and then hit play when you think you've worked it out. So did you work it out? Well, what you hopefully should have noticed is if you add the length squared and the height squared for each row, then that gives you what the hypotenuse squared is. 16 plus 9, most obviously, is 25. And this second one, 144 plus 25, would give 169. And for the bottom one, 81 plus 144, again, would give us the hypotenuse squared, which is 225. And so this, in a nutshell, is Pythagoras' formula, Pythagoras' theorem. And because we're talking about squares, length squared, height squared, and hypotenuse squared, we can literally picture it as squares, like this animation here is going to show us. So if you have a look here, we've got a big square on the big side, and 2 smaller squares on the smaller sides. And what's happening is the 2 smaller squares drain exactly into the big square, which is to say that the smaller square plus the smaller square will always equal exactly the bigger square. And so if we're squaring something, we can picture a square as a literal physical square on each side. And so what we can do is we can set out Pythagoras' formula, or questions involving Pythagoras, into literally drawing sides, drawing squares on the sides of each right-angled triangle. For example, this one here. And so this is the strategy I'm going to show you with these triangles and examples today. So going forward, for any right-angled triangle with shorter sides A and B and a hypotenuse, the longest side of H, the short side squared plus the other side, short side squared, always equals the hypotenuse squared. And so, taking this and rewriting it, we can say that the small square plus the small square equals the big square, as this previous video showed us. 2 smaller squares drain exactly into that big square. And there it goes again. Small square, big square. And so just taking that one step further again, so algebraically, which I'm going to go into in the second video, small square a squared plus the other small square, b squared, will equal h squared. Now you may have been taught this as a squared plus b squared equals c squared. It is exactly the same thing, but over the years I've come to rewrite c as h for hypotenuse. So there's less chance of confusing c for the 2 shorter sides, a and b. Now a few notes before moving on. It doesn't matter which of the shorter sides are a and b in Pythagoras' formula. All that matters is that a and b are in any order the shorter sides. And so all you need to do is not confuse A and B with the hypotenuse. Pythagoras is used when we know two sides of a triangle and you want to find the other side. You're never bothered about the angles in the triangle itself, apart from that you must know one of them has to be a right-angled triangle. One of the angles must be a right angle. So Pythagoras will not work if you don't have a right angle inside the triangle. So it doesn't work for all triangles. Pythagoras only works on right-angled triangles. So let's have a look at some examples. And so let's have a go at finding the hypotenuse. So here's example 1. We need to find x. And so what we can do, as I showed before, is we can literally draw squares on each side of this triangle. And use the idea that the small square plus the other small square equals the big square. And so this one here at the top, if we have a square which is 12 long, we need to be working out the area of it. And so the area of the square is the length times the width, but with a square, all sides are equal. So length times width would mean 12 times 12, which is obviously just 12 squared. So the big square is 144. So we can write this down for the big square at the top. Not the biggest square, but this bigger square at the top. This is the smallest one. And so this one here is 16. Now I've deliberately drawn this horribly. As you can notice here, this triangle is drawn horribly off scale. This says 16, this says 12. Clearly this looks bigger than that one. But the examiner often gets away with this by saying diagram not drawn accurately. So I'm just doing this here, taking it to the extreme. They do that so that you can't cheat by just measuring it. They draw it not very accurately to force you into showing the examiner that you know what Pythagoras is, rather than just measuring the side. Anyway, this smaller side as well is 16 long, so the area of this square would be 16 multiplied by 16, which is 16 squared. Use your calculator, and you'd have 256. And this big square, if it's got side x, the area of it would be x squared. And so if I just write down effectively what we've done here, all we've done is we've done 12 squared plus 16 squared, and so that equals the big square, which is x squared. So 12 squared is 144, 16 squared is 256. And that will together equal the big square, the x squared, if you like. The next thing is to literally just add together these two squares. So 144 plus 256. And so with a calculator, or without, you should find that these two added together give us 400. And so 400 equals x squared. So if we've got a square with area of 400, we need to work out the length of the side, and so the opposite of squaring something is to find the square root. And so x is going to equal the square root of 400. On the calculator, it looks like the tick symbol. Effectively, we're working out what number multiplied by itself gives us 400. So if we try that, the square root of 400 equals 20. And so x equals 20. So I've wrote out where these numbers are coming from, but effectively it's just small square plus small square, and then square root. Let's try another one. Calculate the length of side x. So again, you don't need to do it perfectly like I have in my diagram where you draw the squares on. You could just draw squares like this. And take it from there. But here's a neater version for you anyway. And at this point, if you're wondering, do I really need to draw these squares? No, you don't. I'm just trying to show you a more visual method for Pythagoras, which does involve these squares, which links back to the video I showed you earlier, where the lady's spinning the water wheel, and the two smaller squares drain into the bigger square. This is more a visual application of Pythagoras. And so this one, using the same method, one of the smaller squares is this 12. 12 times 12 is 144. The other smaller square is this one here, which is 5 along. 5 times 5 is 25. Now the big square, the biggest square, will always be attached to the biggest side, which will be the hypotenuse. So this square will be x squared. And so just rewriting what we've done, all we did here was say 12 squared plus 5 squared equals x squared. 12 squared is 144. 5 squared is 25. And that equals x squared. Add these together, we'd get 169. And the final step, as always using this method, is to square root the final number we get. And so x is going to be the square root of 169, which, if you try this on your calculator, tick 169 equals 13. And so x equals 13 centimetres. Right, now it's your turn. So freeze this video now, have a go at these, write down the answers to one decimal place if you need, but I'm thinking you should find all these are whole numbers. So pause now and have a go at finding the hypotenuse for these 4 different triangles. Okay, what you should have found is this. So for the first one, 29, second one, 17, for the third one, 37, and for the fourth one, the hypotenuse was 25. So we've practiced now finding the longest side for hypotenuse, but how about finding a shorter side? Well, finding a shorter side is actually very similar. And so here we've got a triangle, x long, 14 high, hypotenuse is 50, calculate x. We can use the same idea of drawing squares on each of the sides, like so. But what we need to do here, because we're finding a smaller square, this formula needs to be rearranged. And so if I call this square 1, just being lazy and saying S1, and the other smaller square S2, and that needs to equal the big square. Now, as previously stated, it doesn't matter which is the smaller square, as long as these two here are the smaller squares in any order, and not the biggest one. So to find a smaller square, this needs to be rearranged. So for example, if we're finding the first smaller square, we don't want this second smaller square anywhere near it. So this formula can be rearranged by taking away the second smaller square from both sides, or as I think about it in class, it looks like you're swapping the side and swapping the sign. If you get rid of the second square, you can move it to the side of the big square, but if we swap the side, we swap the sign, the plus becomes a minus. And so a small square is going to equal the big square, take away the other smaller square. So I've got this written down in a slightly neater way here. So big square minus a small square equals the other small square. But we're going to do the same thing still. I'm going to work out each of these sides squared. And so this one here, 50 for hypotenuse, this square will be 50 multiplied by 50, which will be 2,500. Now this one here has got length 14. So this square, 14 multiplied by 14, if you use a calculator to check that, 14 squared should give us 200, whoops, obviously can't square numbers, 14 squared is 196. was thinking of 296 for some reason then, never mind. 14 squared is 196. And this one is our mystery one, so let's leave that as x squared. And so just using this formula here, so the big square, 2,500, minus the small square we do know, 196, that equals the other small square, this one here, which is x squared. And so we can actually work out what 2,500 minus 196 is, using one of these things here, which is called a calculator. 2304. So 2304 equals x squared. And then finally, the final step is still to square root the number. So x is going to be the square root of 2,304. Which gives us 48. Answers with Pythagoras won't always be whole numbers, by the way. In fact, it's very rare that they are whole numbers. But for these examples here, many of them are whole numbers. And so x equals 48 centimetres. And so this side here, we've calculated to be 48. Let's have a look at another example. So again, we're finding a shorter side. Again, we've unimaginatively called it x. Find this shorter side. So again, think of the squares on each side of the triangle. And what we'd have, once again, is this square is x times x. This one here is 65 squared, 65 times 65. 65 squared, 4225. And this one on the right hand side, 63. So 63 multiplied by 63, or 63 squared, would be 3969. I'll get into a blue colour so it's not confused with the hypotenuse. So just applying this formula here. So the big square was of size 4225. Take away the small square we could work out, which is 3969. That will tell us the size of the square we're trying to find. So what we need to do now is 4225 minus 3969. minus 3969. We get 256. So 256 equals x squared. And as you've probably guessed, the final step is to square root that final number. So x is the square root of 256. So show this on your calculator, should come to 16, unless I'm very much mistaken. Which for once I'm not, that's a relief. So x is 16 centimetres. So, we've done it where we're finding the hypotenuse, now we've seen it where we're practicing finding a shorter side, so let's put these two together. What if you had a mixture? What if you weren't sure what side you were finding? Are you finding the hypotenuse or the shorter side? So here's a mix of 8 different questions. Now some of these will be decimal answers. Please do use your calculator for them. So you need to find the missing sides, giving your answers to one decimal place where necessary. So for some of these, you'll be finding the hypotenuse, where you add the squares and then square root. Some of them you'll be finding a shorter side, where you do one square minus the other square and then square root. And so this is up to you to decide. And so you need to write these down, think hard, pause the video and have a go at them. So when you're ready, press play and see if your answers agree with mine when we move on. Okay, so those were the questions. Get ready because I'm going to reveal the answers now. And so what you should have found is the answers are these ones in red. And a small thing, but also a not such small thing, just pay attention to the units as well. If these are centimetres in the question, centimetres in the answer. So it might not seem that significant, but it would be a silly mark to lose in the exam if you've done all the hard work and then just miscopy the units. So just do take a bit of care about the units as well as the values too. And so that's that exercise done. So we've been finding a mixture of hypotenuse and a shorter side. So in summary, that's pretty much it, but I want to leave you thinking about if there's another method or not. And so what I've done here is two different examples. We're finding a hypotenuse, the longer side, and on the right hand side we're finding a shorter side. And so if we had a calculator, could we do this a bit quicker, I wonder? And so what we do here is we'd think that the short square, sorry, the small square plus the other small square equals x squared. And so if I just write x squared first, x squared will be 34 squared plus 29 squared. So we could work this out separately and that out separately, add them together and then square root. So let's have a look at that. 34 squared, whoops, 34 squared is 1156. And 29 squared is 841. So we add these two together and then square root. So 1156 plus 841, 1997. Square root 1997. Get about 44.7 to one decimal place. But what I want to think about here is, could we have done this any quicker? Rather than doing the individual squares, then adding, and then square rooting. If we have a look at this here, could we have not just asked our calculator to just square root all of this for us? Could we have maybe done x just equals the square root of 34 squared plus 29 squared? Well, let's see what happens if we were to do that. So tick symbol, short side squared plus short side squared. We actually get the same answer. And that's a lot quicker. So once you've got the mastery, this is what we're going to be looking at in the second video, this quicker method. And so to summarise it in one line, you can make up the hypotenuse by doing the square root of the first short side squared plus the second short side squared. And in a similar way, if you're working out this shorter side here, so going back to the basics, so to work out the shorter side, it's the hypotenuse squared minus the short side you do know squared. It's the big square minus the smaller square equals the smaller square you're trying to find out. And so again, we can work this out separately. So 40 squared is 1600. And 35 squared. What does that come to? It comes to 1225. And that equals x squared. And so if we just do 1600 minus 1225, we get 375. Then finally square root of 375 and see what we get. So the square root of 375 comes to 19.4 centimetres. Whoops! Kilometres, look. It's as easy as that. 19.4 kilometres to one decimal place at least. But again, going back to here, could that have been done much quicker? Well, actually, it could have been. If we just take this one here, effectively, the opposite of squaring something is square rooting it, and so square root x squared is x, square root of all of this should give us the answer as needed, 40 squared minus 35 squared. So again, like we're finding with the hypotenuse, could we have done it just all on one simple line of the calculator? Let's see if we get the same answer. Tick symbol, 40 squared minus 35 squared. Again, does come to 19.4, so this method here is much quicker. And again, to summarise, like I did here for the hypotenuse, if you're finding a shorter side, it's simply the hypotenuse squared minus the other short side you do know, all squared. And so that first video has just given you the basic idea of what Pythagoras is. It's essentially thinking about the squares on the sides. But now you've got that idea, we can now explore this quicker method in the second video, which I'll release at some point, hopefully soon. So I hope you found that useful to some extent. Do feel free to let me know if it's not that useful. Anyway, thanks for listening, and I'll see you soon.